We will now discuss how data, things like text we see in our email messages, images we see off the internet, sounds we hear when we play music on our computer, how data, like that, is represented in the computer. Data is represented in something called binary. Binary is a number system with only two digits, 0 and 1. To understand why computers use binary, let's take a trip back in history. Since the beginning, humans have been looking for tools to help them manage the kind of data they have in their lives, all the way back from early man who used rocks to make marks in the dirt for counting, or rocks to etch pictures on the cave walls to tell stories, to things like the abacus to help with mathematics, to devices in the late 1800s and early 1900s that were quite complex mechanical devices with lots of moving parts to help count and keep track of numeric data. What happened was, in the early to mid-1900s, electricity became viable. And when electricity became viable, electronic devices to help manage the data also became viable. Electronic devices use electricity for most of their operations. Electricity has two natural states. There's either current flowing in the wire, or there's not, and the current can be controlled by a switch. A switch being closed causes the current to flow. A switch being open causes it not to flow. Think of a light bulb in a high school physics class. You connect a battery and two wires to the light bulb with a switch somewhere in the circuit. If the switch is opened, the light bulb isn't lit. If you close the switch, the light bulb lights. So electronic devices naturally have two states. Think of a switch being open or closed, current flowing or not flowing. The two states of electronic devices naturally lend themselves to something like a binary representation where there are two digits. In the rest of this topic, we examine how the data we as humans use, text, pictures, sound, can be represented in binary. To do that, first let's introduce some terminology. We'll refer to a single binary digit, a 0 or a 1, as a bit. Bit is short for binary digit. A byte is simply 8 bits grouped together. A kilobyte is approximately 1,000 bytes. It's actually 2 to the 10th power, which is 1,024. You're going to see throughout the rest of this talk that the powers of 2 are very important in dealing with electronic devices, and in particular dealing with computers. A megabyte is approximately 1,000,000 bytes. It's actually 2 to the 20th power, which is a number somewhere around 1,000,000. So when computer technology talks about megabytes, it's talking about approximately 1,000,000 bytes. A gigabyte is approximately 1,000,000,000 bytes. And you've probably heard this terminology before. If you bought a computer recently, the amount of RAM, or computer memory, is typically in the megabyte range, indicating that a computer has millions of bytes of RAM. And hard drive space is typically measured in gigabytes, indicating that a hard drive has billions of bytes. Exactly what RAM is and why millions of bytes are needed, and what a hard drive is and why billions of bytes are needed, is something we'll be covering in a later lecture. So terminology-wise, again, we see here in the picture that 1 bit, using the idea of the light switch being closed for the light bulb being on and open for the light bulb being off, 1 bit is like a single light bulb. A byte is simply a collection of 8 bits together. And computer technology tends to talk in terms of bytes just for simplicity. It's easier to talk about a group of 8 things than it is to talk about individual things. So really a byte is kind of a grouping for convenience. Okay, let's take a minute and think about the kind of data that we use in our everyday lives when we're working with a computer. And I'll pause for a minute and let you think about it. What kind of data do you work with when you're working with a computer? One kind of data is numbers. So you might use the computer's calculator, or you might run a spreadsheet where the data that the computer works with is actually numbers. Another type is letters. You're typing an email message, an instant message, you're writing a paper in Word, you're working with characters or letters as your form of data. We also use graphics. We've all seen images on web pages. Perhaps you've watched a DVD on your computer, put a picture into a paper that you're writing. You've worked with graphics on a computer. There's also sound. We've all heard the computer make beeps and various sounds, and many people play music, they play their MP3s over their computer. Video is animated or strings of graphics put together to form a video. So you've all seen animations on web pages, and you've probably seen a DVD or a regular video played on a computer. The final form of data that we're going to talk about are the programs themselves. The software on the computer is also a form of data. When you buy a game or you run Microsoft Word, you're using a program, and the program itself is data to the computer. The screen now shows a byte. Here's a byte on a computer. It's 8 bits. That byte can represent multiple different kinds of data. In fact, it can represent any of the kinds of data shown on the screen. Knowing exactly what kind of data that byte represents depends on the context in which the computer uses it. If you're using a spreadsheet program and entering numeric data, then this byte might represent a number. If you are typing into an email message, this byte might represent a typed character. If your computer is playing an MP3, it might be part of a sound. It could be a dot in a... Actually, this byte, under the conventions used by most computer systems, that byte, when treated as a number, would be the number 67. When treated as a letter, it would be the capital letter C. When treated as a graphic, it would be a colored dot on the screen or on a printed piece of paper. When treated as a sound, say if this byte were sent to a speaker, it would be a small fraction of a sound, a decibel level indicating what sound for the speaker to play. When it is data in some kind of a video application, this could indicate one dot in one frame of a video, or this might indicate an instruction to the computer such as add 2 numbers. Again, exactly what that byte represents depends on how the computer uses it. If it sends it to a speaker, it'll treat it as a sound. If you're currently in an email program typing, it'll treat it as a character. Let's take a look at the various forms of data. Here, in the upper left corner, I've listed the forms of data that we've talked about so far: numbers, letters, graphics, sound, video, and programs. We'll now go through and see how the computer represents these kinds of data up here in the left corner, kinds of data that humans want to work with, in the binary that the computer can work with. As we go through this, keep in mind that in essence, a computer is billions of little switches opening and closing, allowing electricity to flow. Now we'll see when we discuss hardware later on that these aren't physical switches. They're not little switches opening and closing inside of a computer. They're actually represented by something called a transistor, which is a solid-state device. It doesn't have a moving part, but it can block the flow of current or allow the current to flow, essentially acting as a switch. So keep in mind that in their essence, computers are billions of these little switches opening and closing billions of times per second. So what we're looking at in this talk is how can we take the kind of data that humans like to work with, the numbers, letters, graphics, sound, video, and programs, and translate them into billions of switches opening and closing. We're going to start with looking at how numbers are represented. We will then look at how letters, graphics, etc. are represented. Now on the previous slide I said that numbers, if this byte were a number, it would be the number 67. Let's see why. To do that, let's take a trip back to, say, 3rd or 4th grade. When you were in elementary school and were learning about big numbers, your teacher probably talked to you about places. So the number here on the screen, 3,192, your teacher might have described as a 3 in the thousandths place, a 1 in the hundreds place, a 9 in the tens place, and a 2 in the ones place. What this really means, the places are powers of 10. So the 3 means 3 times 10 cubed. 10 cubed is 1,000, so there are 3 in the thousandths place. The 1 is 1 times 10 squared. 10 squared is 100, so that's 1 in the hundreds place. The 9 is 9 times 10 to the first power. Remember that anything to the first power is that thing, so 10 to the first power is 10, so the 9 represents 9 times 10. The 2 represents 2 times 10 to the 0th power. Anything to the 0th power is 1, so the 2 represents 2 times 1. This is called counting in base 10. We probably count this way because we have 10 counting states, our fingers. Remember that computers have 2 counting states, the 2 states of electronic devices of being off or on. So instead of counting in base 10, like humans count, computers naturally count in base 2. There are number systems in mathematics for many different bases. Base 2 uses 2 digits to count. Base 10 uses 10 digits. The 10 digits that we count with are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The 2 digits that a computer counts with are 0 and 1. So we said that this byte represents the number 67. Let's see why. To do it, we're going to use a technique similar to the way your elementary school teacher told you to look at a big number. We're going to use places. But instead of them being the tens places, as it is in a base 10 system that we learned to count in, the places in a byte are going to be powers of 2. So this byte will represent 1 in the ones place, a 1 in the twos place, a 0 in the fours place, a 0 in the eights place. You can see a pattern here. The places are doubling as we go to the left. We start with 1, double to the twos place, double to the fours place, double to the eights place. Let's continue. We now have a 0 in the 16ths place, a 0 in the 32nds place, a 1 in the 64s place, and a 0 in the 128ths place. Looking at that, since this is powers of 2, that's 1 times 2 to the 0. Remember that anything to the 0 power is 1, so that's 1 times 1. There's 1 times 2 to the first power. 2 to the first power is 2. 0 times 2 to the second power. Now, that's 0. 0 times 2 cubed, 0. 0 times 2 to the fourth, 0. 0 times 2 to the fifth, 0. 1 times 2 to the sixth. 2 to the sixth is 64, so there's a 64 in the number. And 0 times 2 to the seventh. 2 to the seventh is 128. 0 times that means there's no 128ths. So the way you look at one of these bytes, when translating the byte to a base 10 number, which, by the way, is a very typical kind of quiz question when looking at this stuff, you want to think of it in terms of places. It's the twos places. It's twos, ones, twos, fours, eights, 16s, 32s, 64s, 128s. We're doubling as we go along. And we look for the ones. We see that there's a 1 in the 64s place, a 1 in the twos place, a 1 in the ones place. So 1 times 1, 1 times 2, 0 times 4, 8, 16, 32, a 1 times 64, 0 times 128, that's a 1, a 2, a 64, that's why the byte represents a 67. So the byte we've been working with, if it were being used in the computer as a number, would be treated as a 67. let's look at how you can do this yourself if you were asked to do something like this on a quiz. If you were given this byte, shown here on the screen, and asked what is it in base 10, one way to approach it is to write the byte down and then underneath each of the bits in the byte, start with the number 1 and just double to get the powers of 2. Write down 1, 2, 4, double is 8, double is 16, double is 32, double is 64, double is 128. You then look for where the ones are in the byte. We have a 1 here, a 1 here, a 1 here, and a 1 here. So there's 1 128, there's 1 32, there's 1 2, and 1 1. That gives you 163. So if you're asked to translate a byte to a base 10 or a decimal number, the procedure that is a quick way to do it is to write down under the byte the powers of 2 moving from the right to the left by just doubling, finding out where the ones are, adding them up to get your byte. There's a website that you can use to practice. The website is shown here. If we go out to the website, we'll see that it has a calculator where you can enter binary numbers and it will give you the decimal equivalent, and also go vice versa, which is a topic we'll talk about in a few minutes. So we could put in the binary 11110000 and ask it to translate for us, and the result is 240. Let's try going the other way. What's the byte, the 8 bits, for the decimal number 197? At this point, you might want to pause the lecture and see if you can think about and figure out how to do this yourself. Can you generate the byte, the 8 bits, for 197? Go ahead and pause, and in a moment I'll resume speaking, so after you've tried it yourself, you can come back and I'll show you how to do it. To figure out the byte for 197, you want to remember the powers of 2 that we used in the previous conversion. Except this time we're going to start with the left, which, remember, the leftmost bit in a byte is the 128th place. So we'll ask the question, are there any 128s in 197? And the answer is yes, there's one 128 in 197. So we put down 1 with the remainder of 69. Now we move to in the byte, we move over to the right 1 bit. The next bit over is the 64's place, so we ask how many 64s are there left in the 69 remainder that's still unaccounted for. So how many 64s are there in 69? There's 1, with now 5 unaccounted for. So we move right to our next bit, saying how many 32s are there in 5? There's no 32s in 5, so we write 0, and we still have the 5 remainder. Moving to the right to the next bit, how many 16s in 5? 0 with remainder of 5. How many 8s in 5? 0 with still the remainder of 5. How many 4s in 5? There is 1 4 in a 5, so we put 1, and now our remainder is down to just 1 unaccounted for. Still moving to the right, the next place is the 2's place. How many 2's are there in 1? There's 0 with still the remainder of 1. Then how many 1's are there in 1? There's 1. So now we form the byte by going from the top and reading down, being the left to right of the byte. It's 11000101. And we see the byte written horizontally here. You can practice this at the same website we saw earlier, where it will do a decimal to binary conversion. So we can type in the number 78, and it will give us the byte for 78. We give you the website just so you can practice, because this is a very typical kind of quiz question, either decimal to binary conversion or binary to decimal. And it also gives you an appreciation for what the computer does very quickly internally when you type a number like 78 into a spreadsheet program, the computer has to translate it so that it can open and close switches in a pattern such as the binary shown here. Let's do one more exercise. What is the biggest integer that you can represent with 1 byte? Again, pause the lecture, think about it on your own, and see if you can come up with what the largest integer is that you can represent in 1 byte. And this is one largest base 10 integer that you can represent in 1 byte. I'll now pause, you can think about it, and when you play again, I'll explain how to do it. To get the largest integer that you can represent with 1 byte, first you have to put down what the byte looks like. It's all ones. Now, with a byte with all ones, we can use the technique that we saw several slides ago when we write down the powers of 2. 1, 2, 4, 8, 16. When you do that, 1 plus 2 plus 8, 1 plus 2 plus 4 plus 8 plus 16, all the way up to plus 128, you add them up, it's 255. So the largest integer you can represent with 1 byte is 255. Well, obviously computers work with integers bigger than 255. The reason they can do this is that computers don't use a single byte to represent a number. They will often use multiple bytes to represent numbers. So with multiple bytes you can get very, very large numbers represented. This concludes looking at how numbers are represented in the computer. We'll now move on to the next form of data, which is letters. Letters are represented in the computer using a standard set by the U.S. government. The standard is called the ASCII standard, which stands for American Standard Character Information Interchange. Under the ASCII standard, the byte that we looked at before that was a 67 when treated as an integer is defined to be a capital C. The ASCII standard into their maturity in the 1950s, the military, who were the first developers and main users of computers, had developed several different kinds of computers. The Army had their computers, the Navy had their computers, and since these were in the early stages of development, the Army's computers were developed to represent characters in one way, and the Navy's computers were developed to represent them in another way. The military quickly realized the benefits of being able to share information and decided to standardize how text characters are represented in the computer. So the U.S. government standardization body, the ANSI body it was called at the time, it's now called the National Institute of Standards, the ANSI body stepped in and came up with the ASCII standard and mandated that this be the standard for at least military computers and government computers. The standard calls for 1 byte to represent 1 typed character. As we just saw, 1 byte can represent 256 values, 0 to 255. With 256 possible representations in a byte, there is plenty of space to represent the characters on a U.S. keyboard. You have to represent all the lowercase, the uppercase, the digits, the punctuation marks. With 256 characters, there was plenty of space to do that, so with 1 byte, the ASCII standard could define what each keystroke on a U.S. keyboard should be represented as. Basically, that's what a keyboard does. If you hit a capital C on your keyboard, this byte pattern, the byte pattern we've been studying, gets sent to the computer over the keyboard's connection to the computer. Now there's another standard we should mention here. The other standard is called Unicode. The problem is that the ASCII standard with 1 byte per character was fine for the U.S. keyboard, but as computers became international, people quickly realized that with all the various languages in the world, having 1 byte per character wasn't enough. So the Unicode standard extends the ASCII standard to use 2 bytes per character. With 2 bytes per character, there are hundreds of thousands of representations of characters, which is sufficient to capture languages and dialects of languages throughout the world. The Unicode standard uses ASCII as its first 8 bits, but then with the extra 8 bits can get hundreds of thousands of more combinations to represent other languages. The ASCII definition is represented in the ASCII table, which is in the course readings. Here is the ASCII table. We can see here that in the ASCII table, the standard defines the byte that we've been looking at right here as a capital letter C. And you can see the representation for other capital letters. Over here are some lowercase letters and some punctuations. So this is actually a partial ASCII table. It's not showing all of the characters on the keyboard, but it's showing many of them and the bit patterns that are used to represent them. So we see that the byte we've been looking at could be representing the capital letter C. Let's move on to see how graphics are represented in the computer. Graphics, things like pictures, drawings, are represented by capturing digitally how the image occurs. And we will see that the byte we've been looking at could be what is called a pixel of color in the image. When a digital camera or a scanner captures an image for the computer, they record the color of each picture element. Here we see a picture of a rose, and we see superimposed on top of it a cross-hatching of these cells. Each cell is called a picture element, or pixel for short. These days, if you buy a digital camera, say you buy a 4 megapixel digital camera, we saw earlier that mega means millions. So a 4 megapixel digital camera will be using 4 million pixels, or little grids on the image that it's seeing, to capture the image. Then the computer stores for each pixel a byte value indicating what color that pixel is. So here we see in the picture of the rose that this pixel is white, this pixel is white, this pixel is white with just a little bit of color in the corner, and some of the pixels in here are obviously red, and there are actually different shades of red. The color occurring in each pixel is important because the scanner or the digital camera, whatever device is capturing the image for the computer, needs to record what color it sees in each pixel. The value that it stores in the bytes for each pixel it sees is determined by something called a color palette. So here, again, we see the picture of the rose, and that a little part of it is represented by picture elements, and the format that the picture gets stored in, such as bitmap, GIF, or JPEG, the standard format comes with a color palette saying what byte pattern to put for what color. So for instance, these shades here might have these byte patterns to store. If the digital camera or the scanner sees this color, it'll store this bit pattern, this color will store this pattern, etc. The format that the image is stored in on the hard drive determines both the color palette and what order and how the bytes are put into the file to represent the image. The most basic format of image is called a bitmap image. A bitmap image stores every pixel that the digital camera or the scanner sees. This is called an uncompressed format, and it's the most basic kind of graphic format. We are going to see in the next slide different formats that are compressed and don't necessarily store every pixel like a bitmap. The problem with bitmaps is that they're quite large. If a 4 megapixel camera stored even 1 byte for every pixel it sees, the picture it took would be 4 million bytes, and that's a large picture. Your typical picture coming off a digital camera these days, because it uses the JPEG format that we're about to talk about, might be several 1,000 bytes, not 4 million bytes. Having very large pictures in bitmap format means that they take up more space on a flash card of a digital camera or on a hard drive of a computer, or they take more time if they're sent across the internet as an attachment to an email or as an image appearing on a web page. So for these reasons, bitmap is not used much anymore, although it is the native format that printers need and monitors need to display the picture. It just is not the main format that the pictures are stored in. Pictures are stored in what are called compressed formats. The two main compressed formats in use today are called JPEG and GIF. JPEG is an open standard, and it is now the prevalent standard. It's the standard supported by most digital cameras, and most images you find on the internet are JPEG. GIF is an earlier standard that's actually owned by a company. It's still used somewhat out there. Both JPEG and GIF are what are called compressed formats. Compressed formats do not store every pixel. Instead, compressed formats store patterns of pixels. That's important, so I'll say it again. Compressed formats, like GIF and JPEG, do not store every pixel. Instead, they store patterns of pixels. Let's see an example. Notice the image of the rose and the hashing superimposed over it. Notice that there's a column of completely white pixels here on the left. So there's 4 white pixels. The bitmap format, because it stores a byte for every pixel, would store 4 pixels of white. JPEG and GIF would look for the pattern and say, repeat white 4 times. So instead of storing 4 bytes, all exactly the same, all being all zeros, JPEG and GIF would store 2 bytes saying white and 4, meaning repeat white 4 times. Now, we are seeing this on a simplified image here, but in a 4 megapixel image coming off a digital camera, it's quite likely that there are very large regions of the same color, which would all be the same byte pattern in a bitmap format, and can be compressed down from, say, hundreds of thousands of bytes of the same color to 2 bytes or 3 bytes saying repeat this color so many times. With that, substantial compression can be achieved by the digital camera recording the patterns of the pixel colors instead of every pixel. The amount of compression that JPEG and GIF can achieve and the quality of the image that they store are often a trade-off. The smaller the file, which means more compression, usually the worse the image. The better the image, the larger the file. One extreme is a bitmap, where there's no compression, every pixel is stored, and the bitmap usually is quite clear. Here we can see how the trade-off might occur. In the rose, we would get better compression if we ignored some of the red to get bigger patterns of white. For instance, there are the 4 white bytes here. If we treated these 2 bytes as white, then they could be compressed into the repeat 6 times white instead of repeat 4 times white. But in doing that, we'd be losing a little part of the picture here and a little part of the picture here if we consider these pixels to be white. This would give us better compression, but we would be losing some of the image. We will see when we do some of the applications later on in this course that as we save images, particularly in the JPEG format, part of the save process, in addition to specifying what name you want to save it in, you're allowed to specify what quality you want the image. And most applications usually have some kind of a sliding bar between 0 and 10. 10 being full quality image but almost no compression, 1 being very high compression but usually at a loss of quality in the image. Typically for JPEG images, 60% compression isn't really noticeable for most applications and to the human eye. For instance, 60% compression for an image that will appear on a web page or be printed in a document usually can't be determined by the human eye, and so it's a good level of compression. In the readings, we showed these pictures of a man and his dogs, showing here with 20% compression, we still have very good quality. So from the original image, 20% JPEG compression can barely tell the difference. 40%, still very little difference. At 60%, we start to see a little bit of difference, although it's still hard to see. Here on my screen, and probably on the video rendering that you're seeing, it's still almost imperceivable. But as we get to 80% compression, it starts to get worse. It's still fine to look at. 90% and 95%, it gets grainy and splotchy. You can see in his shirt how splotchy it is. Now, that's 95% compression, so we likely got a very small file to save or to attach to an email, but we did it at the sacrifice of some quality. So this concludes our looking at graphics. In the part 2 of our talk on data in the computer, we will look at sound, video, and programs. Before we end, let's just review what we've seen so far. We went through 3 data types: numbers, letters, and graphics. We see that the translation of these data types that humans like to use into the binary that computers like to use follow standards. For numbers, the base 2 standard, which is all of the binary arithmetic we went through, dictates how a base 10 number is stored in a computer. For letters, we saw that the ASCII standard, or the Unicode standard, determined how letters or typed characters are represented in the computer. For graphics, we saw 3 standards: bitmap, GIF, and JPEG. Now, numbers are not compressed. ASCII and Unicode are not compressed. We also saw that bitmap is not compressed, meaning that for bitmap graphic, every pixel is stored in a byte. But we did see that GIF and JPEG are compressed formats, meaning that when they store the GIF and JPEG images, they're storing patterns, not every pixel. And we saw that 1 byte, the 1 byte we used throughout, if it were treated as a number, would be a 67, as a letter would be the capital letter C, and as a graphic might be a red pixel, depending on the color palette, or a blue pixel, or a shade of red. Again, the same byte can represent all 3 forms of these data. What it actually represents depends on the context in which the computer uses it. In a spreadsheet, that byte might be a 67. In an email program, a typed C. Being sent to a printer might be a red pixel. This concludes the first part of our talk on data in the computer. The second part will go on to address the other forms of data: video, programs, and sound, and we will see that all of them have a similar representation where we have to come up with a standard way of translating the data types that humans want to use into the binary that a computer can use to open and close its billions of little switches.